Alright guys, so welcome back to week 4 of the interactive sessions. We will begin from where we left in the last week, that was week 3. So if you remember, we were discussing certain flows, certain types of flows, which were which we call it as axisymmetric unidirectional steady flows. And one such problem which we saw was fluid dynamics of an extrusion process where we saw that there was a fluid which was which was in between two rotating cylinders. As you can see, the cylinders the individual cylinders possesses their rotational velocities of omega 1 and omega 2, and in order to move the fluid out, which typically is done in an extrusion process, we apply the pressure gradient, which is constant of course, of magnitude minus dp by dz. So necessarily, uh, considering all the assumptions that we saw, we inferred that the flow is going to be a 2D flow in this case, where we will see a non-zero u theta because of the fact that the cylinders are rotating with their own angular velocities, which will also drive the fluid around them. Um, Basically, the fluid that is situated inside the annulus of the two cylinder, uh, on account of viscosity. And since there is also an axial pressure gradient applied in the z direction, the fluid would also tend to move out. But we inferred that these two components of velocities, uz and u theta, they were just function of r, and they were not functions of the theta direction, which we argued that it is because of the fact that the flow is axisymmetric, and also because of the fact that we are looking into a fully developed kind of region where the variables are not going to be dependent on z. So having done that, our objective was to evaluate the velocity profile. That is, we need to evaluate u theta as a function of r and uj as a function of r. And we solved the first bit of the problem, where we started off by writing the Navier-Stokes equation in the theta direction, and then invoking all the assumptions that we considered to simplify the equation into an ODE. And we looked into a special feature of this ODE, which we say that this ODE is equidimensional in nature. That is, all the terms in this ODE bear the same dimension, and to that of these terms, which is u theta, that is the variable of interest. And we say that in the language of mathematics, it is known as these type of equations are known as Euler-Cauchy equation, and sometimes they are also known as equidimensional equations. So the trick that is involved in solving this equidimensional equation is that you need to consider a form of your solution to be some r power k, and then substitute it. And because of the fact that your equation is equidimensional, this r power k comes as a common in all the terms. And since we are seeking for solutions that are non-trivial, r power k, this r power k cannot be equal to 0, and that's why we get the solution for the variable k, which is of our interest. I hope this is clear. And in that context, what we saw is that the velocity profile u theta looks something like this. So it is just some constant times r plus another constant times 1 by r. So this is what the velocity profile actually looks like. And then using the boundary conditions that the so if you remember, the boundary conditions was the fact that at r equal to a, that is, we derive the boundary conditions here. Given that we know that the cylinders are rotating with a constant angular velocities omega 1 and omega 2, we said that the u theta at r equal to a is going to be omega 1 times a, and correspondingly the u theta at r equal to b is going to be omega 2 times b. And just invoking these two boundary conditions in the obtained solution for u theta, we said that the constant a1 and a2 is going to be something like this. Okay, just substituting the boundary conditions in the equations and just solving for a1 and a2 is something that we did. And the complete solution is just the complete solution for u theta is just a1 times r and then 1 by r times a2. That is something that we got. So basically, if we just write it down, uh, meaning that if we just write it down, u theta as a function of r, my a1 is just omega 1. I hope this is clear. So a1 is just omega 1 minus p2 square by sorry, v square by d square minus a square. This is a1, and there is the multiplication of omega 1 minus omega 2, and then this a1 is multiplied by r, and then we have plus 1 upon r, and my a2 is going to be just this, so it is just a square v square omega 1 minus omega 2 divided by v square minus a square, where this a and b are the individual radii of the inner and the outer cylinder respectively. Okay, so this is the complete solution for u theta, as you can see in the screen, in my screen. And I hope the methodology used for deriving this solution is clear to, clear to you guys. All right. So what now we need to do is, I said that we'll be looking some very special case of this solution of u theta. But before that, let's first go ahead and derive the, and just find out the uz velocity profile, because remember, we also need to solve for uz. And once we are done in solving that uz, I will show you some special cases of these velocity profile, and which have some very fascinating inferences from this form of the velocity profile of u theta. Okay, but before that, I'll stop here for some time first of all, and once things are clarified, I will first go ahead and solve for the uz velocity profile, which is of course again a function of r from the z momentum equation. And then once we do that, we will come back to this u theta form of the velocity profile to obtain certain inferences by considering some special cases of this problem. Okay, I hope the exercise is clear. What we need to do. So I'll just stop here for a couple of minutes, just for you guys to actually kind of brush up to the things that we did so far, and then also to think about how to basically proceed in order to obtain the uz velocity profile, that is the velocity profile in the z direction. Okay, all right. So if no questions, then let's go ahead and solve for the velocity profile in the z direction, for which we need to use the Navier-Stokes equation in the z direction. And if we write down now, so we have done this now many a times, that writing the full Navier-Stokes equation and invoking the assumptions to get the simplified form. So I will not start from the beginning, that is the main PDE of the Navier-Stokes equation in the z direction. Instead, this I will leave you as an exercise to try it at your home, that write the complete Navier-Stokes equation in z direction, invoke all the assumptions that we consider in this problem to basically get to the simplified form of the z momentum equation. Okay, so I'll just write down the simplified form. I hope you understand what I'm trying to say here, and I hope you understand what I asked you to basically do. So I'll just write the simplified form. So what to write basically, Navier-Stokes equation in z direction. I'll just write simplified by invoking all the assumptions. Assumption means, for instance, those assumptions like the flow is steady, it is axisymmetric, it is fully developed, and all sort of this. Okay. And of course, coupled with the fact that we have also used the continuity equation, which now says that my ur is not going to be a function of r, or it says that my ur is basically equals to 0. That is something that we got from the continuity equation. And using all those assumptions, the z direction momentum equation simplifies to something like this. So it just simplifies to minus dp dz plus mu times 1 upon r ddr. Needless to say, of course, it will now turn into an ODE, and this is something that we have seen repeatedly. And this basically looks something like this. So it is r times d of uz by dr And then this is equals to 0. All right, so this is the simplified form of the z direction momentum equation, or in other words, the Navier-Stokes equation, by invoking all the assumptions that we considered. Okay, and the variable of interest is of course the uz, which is just going to be a function of r, and this is something that we now want to calculate. But before that, since we know that there is an applied pressure gradient which is reflected by this term minus dp dz, and we know that this is just a constant, so what I will do is I'll just replace this. So just for the sake of repeatedly writing minus dp by dz, I just replace it as some g. So if I say g, it is just the constant pressure gradient that I'm considering in my analysis, where g is nothing but minus dp by dz. So this equation then just simplifies to, I hope you now know, I mean, you are experts in solving these kind of ODEs. So this is just 1 upon r ddr of r times dqz by dr. And then this just comes out to be equal to minus of g by 2 mu, where I say that g is nothing but minus dp by dz. All right. So okay, so let's solve this. So this as you can see is a second order ODE, meaning that we will inevitably get two constants, and we will see what those constants will be. But first let's integrate and solve this. So before integrating, I just write this term as ddr of r times duz by dr, and then this term becomes minus g by mu times r. And now let's integrate. So if I integrate this, let's integrate it with respect to r. If we do this, so let's see what constant did we use here. Okay, we use there a1, a2. So here we will be using v1, v2. So if I integrate this with respect to r, what I get is I get r times duz by dr, and then this becomes minus g by 2 mu r square plus v1. And before integrating, again, what I'll do is I'll divide the entire equation by r, which means I just get duz by dr, and this just becomes minus of g by 2 mu r plus b1 by r. And then now if I just integrate it again, integrate with respect to r, what I get is I get the velocity profile uz of r, because this is something that I get if I just integrate this with respect to dr. I'll just get uz of r, and then this term, the first term becomes g by 4 mu r square plus v1 ln r plus v2. Typically, because the integration of 1 upon r dr is equal to ln r, and I have a constant v1 here. That's the reason why we get this ln r kind of nature in the solution. So that's it, guys. So that's the solution for uz of r. And now, as we do, the common practice is to evaluate the constants v1 and v2, for which again we'll be using the boundary conditions for uz basically. And this is something which is important, because we now need to think what boundary condition does uz satisfy in order to evaluate the constants v1 and v2. So for that, I would like to take you guys to the physical picture. So what I see is that in my problem, at the surface of the cylinder, I could see that because of the fact that there is a viscosity of the fluid, and because of the fact that we are using something which is known as the no-slip boundary condition, the fluid which is adhering to the surface of these cylinders, for instance, the inner cylinder bearing radius A and the outer cylinder, bearing radius B, it will just have a rotational velocity of omega 1 times A and omega 1 times B respectively. Meaning that because of the fact that we are using, because of the fact that, the fluid is viscous, and using the idea of the no-slip boundary condition, the only velocity that a fluid layer that is adhering to the surface of the cylinders having radius B and radius A respectively is just the u theta component of velocity, which means that the uz component of velocity at r equal to A and at r equal to B is essentially 0. And this is the consequence of the no-slip boundary condition. I hope you understand what I'm trying to say here. So So I'll write it down that because of the no slip boundary condition, okay, my uj at r equal to a and my uj at r equal to b, this is just going to be equal to 0. Okay, and this is again because of the fact that the fluid layer, as I explained, the fluid layer that is adhering to the surface of the cylinder will just have a rotational velocity of the cylinder itself because of the no slip boundary condition. Okay, and that velocity of course is in the u theta direction because the cylinders are rotating in the u theta in the u theta uh, in the u theta direction, of course. So this means that I can write that at r equal to a, I have uj at r equal to a is 0. This is something that I already wrote, and and if I just use this, so if I just use this, so let's name this equation. If I had given some name, I don't know, maybe. Okay, I have not named any equation yet, but I hope you understand what I'm trying to say here. So if I just use this, that at r equal to a, uj is 0, I'll just get 0 equal to, minus of g by 4 mu a square plus b1 ln a plus b2. Okay, and at r equal to b, my uj is also 0. Okay, which means I can just write this like this as 0 equal to minus g by 4 mu b square plus b1 ln b plus b2. All right, so that's it. That's it. Two equations and two unknowns. That is b1 and b2. That's all that we need to do. So if I just so what can I do? I can just subtract this equation from this equation, and then I'll get b1, and then I use the value of b1 in one of the equations to basically get the value of b2. That's all that we need to do. And I think you are experts in doing all these things. So the detailed algebra I'll of course not show here because I have already calculated this in my end. But that's the simple thing that you need to do. I mean, just solve for b1 and b2, two unknowns and two equations. That's it. So if you do this, so if you do the math, you will see that your b1 comes out to be equal to g by 2 mu a square minus b square by ln a minus ln b. Okay, and your b2, this will come as g by 4 mu a square plus a square minus b square by ln a minus ln b. Ln a minus ln b, you can write it as ln a by b. That's up to you. And then this times ln a. So that's it. That's the constants b1 and b2. So therefore your uj is just this velocity profile. So therefore uj is just this. So that's it. Because uj is just this term where b1 and b2 are given by these values, which is of course in terms of the applied pressure gradient and the radii of the two cylinders. Okay, so that's it guys, we have completed the problem. We have solved for the two velocity profiles, u theta of r and uj of r, and we obtained an expression. So we solved the theta momentum equations and the jet momentum equations separately. Luckily we saw that because of the fact that the pressure gradient is constant, and we didn't have any pressure gradient in the theta direction, the theta momentum equations and the jet momentum equations are essentially decoupled, which means that the theta direction velocity is independent of the jet, and the jet direction velocity is independent of theta. And again, you can appreciate that this is something, again, the linear superposition that I was talking about, that if your governing equations are linear, then you can always decouple this problem into two simpler problems. For instance, we could consider two problems now that there is no applied pressure gradient and the cylinders were just rotating with omega 1 and omega 2, plus another problems where the cylinders were fixed and there is just a flow that is being generated inside the annulus by a constant pressure gradient of dp by dj. So the solution, as you can see, is just the linear superposition of this. So your velocity profile. So your velocity profile now, u is just the u theta, which is a function of r e theta hat plus uz, which of course is a function of r again, times ez hat. That's it. That's your velocity profile that the problem wants to evaluate us for. All right. So we have finished solving this problem, but as I said, we will look into certain special cases of the theta direction velocity profile in particular, because the z direction velocity profile is not of that. So this kind of velocity profile you typically get when there is a flow taking place to an annulus because of a pressure gradient, and it is not of great significance. But the theta direction, of course, it bears a significance because you're moving the fluid out. But I am saying that I mean, what to say? I mean, interesting physics more interesting physics can be understood if we consider certain special cases of the u theta, velocity profile. So we will see into that. But before that, I'll stop here for a couple of minutes, and if you have any questions, you can ask, and then we will see certain special cases of this flow. So we'll go to the next to this week's notes, and then we will see these special cases. But before that, if you have any questions on how did you obtain these velocity profiles and all, you can feel free to like ask here or post it in the discussion forum of the course. So this is just the same problem. We'll just look into certain special cases, and I'll clarify you what the special cases are, and then we will see the interesting aspects of these cases. But just before that, just you know for completeness, I will just write down the u theta velocity profile, which was just omega 1 minus b square by b square minus a squared times of omega 1 minus omega 2. This is times r plus 1 upon r. This is a squared b squared by b squared minus a squared times omega 1 minus omega 2. Okay? All right. Okay, so if no questions, so now what we will do is we will first consider the fact that the applied pressure gradient, which is just dp by dz, we will just turn it off. So we'll switch off the applied pressure gradient, meaning that now I just have a kind of a 1D flow. Uh, 1D flow meaning that I have a fluid which is just moving in the u theta direction, which is varying along r, of course, but it's kind of a 1D kind of flow that I'm considering, because of the fact that I will no longer have the uz component of velocity, which was present due to the applied pressure gradient. So I hope this is clear. So what we will do is, in the previous, I mean, in the completed problem that we saw, we had the rotations of the cylinder as well as this applied pressure gradient. But now for the special case, we will switch off the pressure gradient and just analyze the u theta, just analyze the dynamics in the theta direction. That is something that we will see now. So that's what we will do. So we'll say that the applied pressure gradient is 0, meaning that the fluid will no longer have a velocity in the axial direction of the flow. Okay. If this is the case, that I now just need to see the u theta as a function of r component of velocity. Of course, the boundary conditions and all are still the same for u theta, meaning that I can use this solution of u theta that we, I mean, derived it in the previous week, which, as you can see, is a function of the rotational velocities of the cylinder, their differences, and the radii, that is b, that it depends on the value of b and a. Okay. Now, so what we will do is we'll consider the first special case. So the first special case is, we will say that my omega 1 is equal to omega 2, and this is equal to some omega. Meaning that what happens, we want to look into the scenario in which both the cylinders having to different angular velocities initially. Now what happens if I say that they bears the same angular velocity, that is, if that is the first cylinder and the second cylinder are rotating at the same are rotating at the same angular velocity. We want to explore that scenario. And the same angular velocity which I was saying, I would say this is some omega. This is some omega, which is a non-zero quantity basically. So in that case, if I just substitute this in this expression, what I see is, you can very nicely see that this omega 1 minus omega 2 and these terms would simply go out, which means I just have that my u theta, which is a function of r, is equal to omega 1 times r. That's it. Because since these are equal, this term and this term would basically go, and I will just have omega 1 times r. And since omega 1 is equal to omega 2 is equal to some generic omega, I can just now write that u theta as a function of r is omega times r. So this is what my u theta you know turned out to be, if I consider that both the cylinders having radii a and b are rotating at the same angular velocity omega. Okay. Now, before proceeding, I would look into a second spatial case. I hope this is clear. We are just substituting the value of omega 1 and omega 2 into this expression of u theta. That's it. That's all what we are doing. Okay. Now, in the second spatial case, I hope the first spatial case is clear. So I'll write it down here. So in this case, both the cylinders are rotating with the same angular velocity. Okay. Now, let's, before looking into this solution and the consequence of this solution further, I'll consider a second special case. The second special case is, what happens if I don't have the inner cylinder, meaning that my A becomes equals to 0, which means that the inner cylinder's the radii of the inner cylinder tends to 0, or meaning, or physically I don't have the inner cylinder. That's what I'm saying. And if I don't have the inner cylinder, this will automatically mean that my omega 1 is basically equals to 0. That's it. So the second special case is that when the inner cylinder is absent. Okay. All right. Now, if this is the case, and then if I just substitute it again here, I will see that I don't have an omega 1, meaning that these two terms will be 0. My A is basically equal to 0, meaning that this term will entirely go to be equal to 0. I will just have a b square by b square minus omega term, and this will just give me 1, meaning that the u theta, okay, as a function of r, will just now turn out to be omega 2 times r. Just substitute these omega 1 equal to 0 and a equal to 0 into this expression. That's all that you'll get. So, and if I say that my omega 2 is just some generic omega, because now I just have a rotational velocity of just one cylinder, I can also say that my u theta is just omega times r. So that's it. So you can see that in these two special cases, so what did we do? We just considered two special cases. The first case, when there were two cylinders of distinct radii and both the cylinders were rotating with the same angular velocity. And in the second case, I said that the inner cylinder is absent and the outer cylinder rotates with some generic angular velocity omega. And in both this scenario, what I saw is my velocity profile in the theta direction is just that omega multiplied by r. And I hope you can appreciate that this is nothing but the tangential velocity of the fluid. That's it. So you can now see that in these two cases, okay, the tangential velocity of the fluid is omega times r, which means that all the fluid particles are rotating with the same angular velocity omega about an axis, and that axis is nothing but the z axis here. This statement is very, very important. What I am saying is that in these two special cases, the special cases of the case 1 and case 2, where again I repeat, the case 1 is the fact that I have two cylinders of two distinct radii, and both the cylinders are rotating with the same angular velocity omega. And in the second case, I don't have the inner cylinder, but the outer cylinder is rotating, containing the fluid inside. The outer cylinder is rotating with some angular velocity omega. And in these two scenarios, I found out that the velocity profile in the theta direction, u theta, is nothing but omega times r, which means that all the fluid element, okay, are rotating about an axis with the same angular velocity omega. And in that context only, we can say that the tangential velocity will just now become omega times, will just become omega times r. And this is known as rigid body motion. Okay, and in the language of fluid dynamics, this is something which, so this scenario, the special case 2, and also the special case 1 also sometimes, this is known as a force vortex. And in force vortex, you can show that your velocity profile is proportional to r. That your velocity profile, of course, in the theta direction is proportional to r, and this is something that we are getting. So it's a force vortex, and the motion of the fluid elements are known as rigid body motion. Now we will see why this is called rigid body motion. Okay, very shortly. But I hope the what to say, the justification of these two cases are clear to you, that why this is called, so we will see and we'll prove mathematically that indeed this is a rigid body motion. That means all the fluid elements are just rotating without undergoing any deformation. It's just like the fluid is just behaving like a solid body which is rotating around an axis with some velocity omega. That is why it is called rigid body motion. But we will also prove it that it is indeed a rigid body motion, meaning that we will see that there are no stresses. The stresses in the fluid, at least the extensorial or the tangential stresses are just zero, or the deviatoric stresses are just zero. Okay, and we will see and we will prove that why this is called a rigid body motion. But at least the terminologies that I use, that the rigid body motion and the fact that this is called as this kind of flows are called as a force vortex flows. I hope this is clear to you. Okay. uh, so now, if this is clear, what I will do is, in order to prove that this is indeed a rigid body motion, what I will now do is, because I know that the velocity profile in either of these two cases, either case 1 and case 1 or case 2, is just omega times r, what I will do is, I will now try to find out how does pressure vary in the radial direction. And this will give us a hint so as to why we call it as a rigid body motion. Okay. So for that, what I will do is, in order to evaluate the pressure that is varying in the r direction, I will write down the Navier-Stokes equation in the r direction. So if I write down the NS equation in r direction, so what do we get? I hope you are with me on this so far. So if I just now write the Navier-Stokes equation, so okay, so I'll write down the complete Navier-Stokes equation, and then we will see the assumptions, just for you guys to get the heads up of the things that we are doing. But again, these are the things that we have done repeatedly till now, at least in this course. So the first term is del ur by del t, then the term is del ur by del r plus u theta by r del ur by del theta. Okay, and then I have what? I have uz times del ur by del z. That's the inertia term. Okay, I also have one more term which is just minus u theta squared by r. Okay. Okay, so this is the inertia term, and then the viscous term is minus of del p by del r. That's the pressure gradient times mu into del r of 1 upon r del r of r ur. Okay, and then I have what? I have plus 1 upon r squared. Okay, del square ur by del theta squared minus 2 by r square del u theta by del theta plus del square ur by del z square. Okay, so again, this is the full Navier-Stokes equation. I'm just writing just to give you a flavor of how the Navier-Stokes equation in the r direction look like, because we have seen how the Navier-Stokes equation in the theta direction looks like when we derive the solution for u theta, and when we derive the solution for uz also in this case, and also in the previous flows that we saw, at least in the theory classes, and in the last tutorials, we saw how to write the Navier-Stokes equation in the z direction. So for now, just for the sake of completeness, I'm just writing how the Navier-Stokes equation in the r direction basically looks like. Okay, now let's invoke the assumptions that we use. So the first assumption is in fact the fact that I don't have any ur component of velocity, meaning that all these terms will just go to oblivion. So this is just this is just 0, and this is also 0, this is also 0. This term is, however, non-zero, okay? And this term is essentially the main crux of this exercise. But let's first delete all the terms which are not there. So ur is just 0, ur is just 0. And this term is also 0 because I know that my u theta, is just the omega r, which means it is not a function of theta. And also we saw that this is essentially a consequence of axisymmetry. And I have a ur which is 0, which means that if I just now rearrange all the terms by invoking these assumptions that I just now considered, I just have 0 equal to minus of del p by del r plus what? Okay, that is not 0 because I have a term here which is minus u theta squared by r. So I just have this, which is minus of 2 theta squared by r, and then I have minus del p by del r plus, I think all the terms here is just 0 in this term basically. So this is just 0, which means I just have, and of course the fact that my pressure is not a function of theta and z. Pressure is not a function of theta, that we already saw, because of the fact that my problem is axisymmetric. Pressure is not a function of z because I say that my pressure can be a function of the z. Maybe because, okay, so it's not you know it's not so trivial to write this, because of the fact that my dp by dz is constant. So it's like dp by dz is essentially a constant which was g. So this means that if I integrate it, I just have pressure which just varies linearly with g. Okay, so at least I know that my pressure is not a function of theta. Pressure can be a function of z. If I have a you know if I have a background flow, which is, if I have a background pressure gradient which is actuating the flow. But in this case, in these two special cases, I consider that this term essentially is 0. That means that my flow is just generated by rotating the two cylinders, which means I can also say that my pressure is not a function of z. I hope this is clear. So in the earlier problems where the flow was actuated by two mechanisms, the rotation of the cylinders and the axial pressure gradient, in that context, my pressure can be a function of r and z. But here, since I am looking into the special case that the flow is just being generated by the rotation of the two cylinders and there is no axially applied pressure gradient, I can be rest assured to say that my pressure is not a function of theta and z, which means this minus del p by del r can be now written as a complete derivative, which is just, or an ordinary derivative, which is dp by dr. And then I can just say that under these circumstances, when my velocity is just u theta, my dp by dr is equal to u theta squared by r. Okay, and I know that my u theta is what? U theta is just omega r, right? So it becomes omega r. Either I consider the first case or I consider second case. But the first case, as I repeat, was the finite rotation of the two cylinders bearing the same angular velocity, and the second case was that there is no inner cylinder and the outer cylinder just rotates with some omega. And in these two cases, I saw that my u theta is just omega times r. So if I just substitute this here, I can say that my dp by dr is equal to omega squared r squared. Okay. I think I did a mistake here. There also not a mistake, but I missed the rho here. Remember, there is this rho term here. So this rho will also get multiplied with this, which means that there will also be a rho here, and there will also be a rho here. Okay, so it just becomes rho times omega square r squared by r, which means my dp by dr is rho omega square r, or you can write it as rho r omega square. All right, so this is what, and this is how my pressure would essentially and only vary in the r direction. But but that's it. That's what the math says. But if you just carefully have a look at this term, so what is this term? Is it not? So if you compare it with this term mr omega square, what is this? This is essentially the centrifugal force. Okay, this is essentially the centrifugal force if you are looking into the system from a non-inertial frame of reference, and since the fluid is itself rotating, we are in kind of a non-inertial frame here. I mean, of interest. So the frame of interest is the non-inertial frame, and in this case, you can see that this is nothing but the F centrifugal that comes into this picture. Okay, centri. So I'll just write it as F centri basically. So if m r omega square is your F centrifugal, so if I just divide it by divided by the volume of the fluid, let's say, then this just becomes, so F centrifugal per unit volume of the fluid is just rho r omega square. So this is nothing but your centrifugal force per unit volume. That is something that I want to infer here. So this is your centrifugal force per unit volume. But what we saw is that the pressure gradient in r direction, if there is a rigid body motion, is being balanced by the centrifugal force. That is something that you must realize. And what does this actually mean? This actually means that if I now kind of draw the streamlines, for instance, I'm drawing the streamlines for case 2, where there is no inner cylinders and the outer cylinder is just rotating with some omega. Okay, so if I just now draw the streamlines, okay, so the outer cylinder is rotating with some angular velocity omega, meaning that how the streamlines would look like. Okay, so let's draw this cylinder with some different color, maybe black. Okay, and this was rotating with some omega, or it was rotating with this omega maybe, and then the axis of the cylinder is kind of like this. So let's say I'm looking this. So let's say this is my x-axis and this is my y-axis, and this happens to be the r. So your theta is essentially this. This is basically your theta direction, or I would say, yeah, so this is basically your theta direction. So now if I want to draw the streamlines, I would say that one of the streamlines would look something like this, which are just concentric circles. I hope you can imagine what I'm trying to say. So the streamlines are just concentric circles, for instance. And I know that at any point of the streamline, if I draw the tangent, I get the direction of velocity. And of course, the direction of velocity is tangential, which means that if I draw a tangent here, this gives me, the direction of u theta. If I draw a tangent here, this gives me the direction of u theta, and so long and so forth. For instance, if I draw a tangent here, this will give me the direction of u theta. And what else do I know? I know that u theta is just omega r, which means if I want to plot, if I want to plot the variation of the theta direction velocity, I can just now draw it something like this. So u theta at let's say, so what would be u theta at r equal to b? So here it would be just so u theta is just going to be omega times b, and it is going to vary something like this, such that the velocities are tangent to these streamlines. I hope you can appreciate what I am trying to say. Okay, so this would be my variation of the u theta. So this is nothing but your u theta as a function of r. Okay, and similarly this is axisymmetric. So if you move around this axis, you will see the same u theta when you basically get a full circle. So this is how, so this is, of course, this is for the case 2 that I'm showing, meaning that if there is no inner cylinder, the same analogy goes, also holds good if I have a cylinder of, finite, if I have also have a cylinder of finite, let's say, radius A, then, I'll have only this section of u theta. That's it. The velocity here would be just omega times A, the velocity here would be just omega times V, and I'll just have these, just this section. So I hope you can now draw the, the similarities between the special case 1 and the special case 2. Okay, now this is what, the full picture. And of course these kind of flows, as I said, these are known as vortex flows. Of course, these are more in particular, these are known as force vortex, and in force vortex, okay, as I said, that the pressure, that is the pressure in the radial direction is being balanced, okay, by the centrifugal force. And you can actually prove this by, drawing a, let's say I'm considering a fluid element, which is somewhere here. Okay, let's say I'm considering this fluid element, and if I just, zoom in this fluid element, so the thing is, if I kind of, zoom into this fluid element basically would look something like this. Okay, now what we saw is that my dp by dr is nothing but, it's just the centrifugal force per unit volume, which is rho times omega times r squared, which means that, and of course you can now infer that this rho, that is the density of the fluid, which is greater than 0. This r squared is a term which is greater than 0, and for the sake of, or, without losing any generality, I am considering that my omega is also a term which is greater than 0, meaning that my cylinders are rotating in the plus, e theta direction, which is in this manner. Okay, that is in anti-clockwise direction, because since theta is considered here, since theta is considered in an anti-clockwise direction, so the velocity of the cylinder in the same sense of theta is just going to be positive, which means that my omega is also a positive quantity, which means that my dpdr, that is my dpdr, is basically equal to, so this is greater than 0. So now if I move in the radial direction, what I want to see is now is that in this fluid element, if I move in the radial direction, okay, my dp by dr is essentially positive in this direction basically. So if I draw the pressure forces in this fluid element, you can see that the forces, here, the pressure forces here are going to be larger in magnitude than the pressure forces here. Okay, which means that in the negative r direction, that in the negative er direction, there is a net pressure force, which is acting in this direction, and I'll call it as fp. Okay, now in order to balance this net pressure force, we have this centrifugal force in this inertial, in this non-inertial frame of reference, and this centrifugal force basically, acts in this direction. This is your f, so I would call it f centri, and these are per unit volume. Okay, I hope you realize. So this fp is the force per unit volume, this f cent is also the force per unit volume. So actually there is a balance between the pressure force, which the net force is acting in this direction, to the centrifugal force, which is basically acting in the radial outward direction, and this balance is maintained in all fluid elements. But the important thing to realize is that even though there is this balance, the fluid elements do not deform, and we will see shortly why the fluid elements do not deform, but they move with the constant angular velocity. And these kind of thing that, and also you can infer, you can always, realize the fact that whenever the streamlines are, curved, pressure is always balanced by the centrifugal force. That is something that you need to realize. Okay, pressure or the pressure gradient or the force due to the, or the pressure force is always balanced by the centrifugal force. Okay, now the second thing I said that in this, since these kind of motions are also sometimes called as rigid body motion, meaning that the fluid element that I draw here and all the subsequent fluid element that I just now, drew here, they won't basically deform. It's just like they behave as a solid body rotating around a fixed axis with some angular velocity omega, meaning that there is no deformation of this fluid element. That is something that so for instance, if I draw a fluid element, the fluid element here would also look something like this. The fluid element here would also look, something like it. There is no, deformation of this fluid element, and that can be very easily inferred if we calculate, let's say let's say tau r theta component of stresses, because the deformation in this context can only be reflected in the tau r theta component of the deviatoric stress. Okay. uh, and as you know, the tau r theta stress component would look what it is, just del r of r times del r of u theta by r, because once I know u theta, I can always calculate the stresses basically. Okay, so it is 1 upon r times del ur by del theta, and since I know that this term is just 0, my tau r theta is equal to r times del r of u theta by r. Now, in these two special cases that I consider, I know that u theta is what? U theta is just omega times r, right? Which means my u theta by r is just omega. Which means that if I just substitute this u theta by r in this expression of tau r theta, I will have tau r theta equal to r times del r of omega. So what is this? Omega, as you know, is just the constant angular velocity of the cylinder, which is just a constant, which means that this del r of omega is just going to be equal to 0, meaning that my tau r theta, which is responsible for what to say. So since this tau r theta is responsible for changing the shape of the fluid element, or elonging, or squeezing the fluid element, since this it itself is 0, meaning that my fluid elements will not get deformed now. And this is the hallmark of a rigid body motion in force vortex basically. So tau r theta is equal to 0, and this indicates rigid body motion or rigid body rotation, meaning that once again I repeat. So what are the features that we saw in rigid body rotation or rigid body motion? My u theta is just omega times r, that is the tangential velocity. All the fluid element doesn't change their shapes. Okay, they just behave like a solid and rotate with the same angular velocity omega about an axis. So I hope you realize that that the direction of this omega is perpendicular to the xy plane, that is along the z axis, which is of course perpendicular to the plane of my writing device. Okay. All right. So this is something that I want. So this is something that I want to convey to you by considering these two special cases. And I hope you understood what essentially meant by rigid body motion, how the pressure gradient, whenever the streamlines are curved, the pressure gradient is always balanced by the centrifugal force in rigid body motion at least. And then you saw that how this balance is established here. Okay. And also the fact that that my tau r theta is basically equal to 0 indicates that indeed I have no deformation of the fluid element, meaning that the fluid element shape would remain intact and they would just behave like a solid body. Okay, so that's the thing. But remember, the flow is not irrotational. That is something that you need to understand. Although the fluid elements do not change their shape, the vorticity of the flow is not 0. That is something that you need to realize in case of force vortex, because you can see that they are indeed rotating with a constant angular velocity omega. Okay. All right. Also remember, since I in force vortex, in scenarios of force vortex, my tangential velocity is always proportional to r basically. That is something that you need to realize. And that of course we derive that if we look into the special cases, my u theta is indeed omega times r. All right. And this is how the velocity profile essentially would look like. This is for I'll write here, this is for the spatial case 2. Similar analogy can be drawn for the spatial case 1. The velocity profile would exactly be the same, just that I will have a solid cylinder here and I will not have these profile of the velocity. Rather, the velocity profile will start from here and vary something like this with the same exact magnitude. That is something that I want to infer. But remember, the spatial case 1 is the very case when the cylinders are rotating with the same angular velocity. If the cylinders rotate with a different angular velocity, then the fluid element will deform and this is no longer a rigid body motion. And such type of flows is known as Taylor-Kuet flows. It is named after the great G.I. Taylor, who worked on many of these kind of flows, axisymmetric flows. And in fact, there is also a very famous I mean famous stability analysis of these flows. It is known as Taylor stability. That is the stability that people assess the stabilities of that. So it is shown that if the rotational velocity of the cylinder exceeds a critical velocity, then this flow gives rise to instabilities. Okay, and these kind of instabilities are known as Taylor instabilities, named after again the great G.I. Taylor. And we will not look into these instability at least now, and of course, like later on when we'll be looking into hydrodynamic instability, we will we will not look into that instability now, but just for a know-how, I just say that how rich the literature is in terms of Taylor Twite flows. All right. Okay, so this ends the discussions on axisymmetric flows through pipes, and we'll stop here for a couple of minutes, and in the next half of the discussion we will look into something which is known as scaling analysis in fluid dynamics, and we will see that this indeed has important implications in solving fluid dynamics problems. Okay, but we will stop here for a couple of minutes just for you to digest what we have done so far and kind of reflect on the analysis that we did. So I'll just write down the topic. So we'll do the scaling analysis of hydrodynamic equations. Okay. So before starting this, so this is the second agenda for this session. But before starting this, I'll stop here for a couple of minutes. I'll come back by just filling my mug. Till then, like if you have any doubts, you can ask, and I'll just come back in a minute or so. Okay. All right. Sorry for the interruption. So, so now I hope the analysis of axisymmetric flows are clear. So we looked into a very generic problem, where where we basically solved the Navier-Stokes equation in the theta and the z direction, and that and then we invoked the assumptions to basically solve for the velocities u theta and uz. We looked into the special cases of force vortex, where my u theta is basically proportional to r, which is nothing but omega times r, that is the tangential velocity, and we argued that this is indeed the case of a rigid body motion. Okay, now we'll look into, so what we will do now is we'll look into a very special concepts in fluid dynamics, which is known as non-dimensionalization. Meaning that what we'll do is, so far the governing equations that you wrote, for instance, the continuity equation or the Navier-Stokes equation in the x, y, and z direction in particular, these equations has certain properties. Like for instance, we have the density, we have the dynamic viscosity multiplied with the viscous term, and density is multiplied with the inertia and the body force term. So what we will do is, we will see that in certain instances, while we are trying to solve the fluid dynamics problems, at least from now on, for instance, we will look into a problem in the next class, after we learn this concept, is like solving a transient flow through a pressure driven pipe, or through a pressure driven channel basically. I will look into that. We'll look into the transient case of that problem, and also we'll look into something which is called as an oscillating pressure gradient flow in a circular pipe and things like that. So these are some more advanced and complex problems involving the Navier-Stokes equations. But the central understanding is that if we kind of non-dimensionalize the equations rather than dealing with dimensional quantities, it becomes easier for us to see how a particular quantity essentially varies. Meaning that, for instance, if I ask you that solve the Navier-Stokes equation, and you obtain a velocity profile, and tell me that, give some physical inferences of this velocity profile, that what happens when a particular quantity is increased, what happens when a particular quantity is decreased, and how it is reflected in the velocity profiles in your solution, is something that I'm asking. Now, in this context, it becomes easier for us if we non-dimensionalize our equation, because I can say you that what happens when that. So if I say you that vary a certain quantity and give me how the velocity profile changes. Now you of course end in a dilemma. The fact is that you ask me that should I vary the density, or should I vary the viscosity, or if there are any other parameters that are coming. But you will see that if I non-dimensionalize the equation, I will just have one parameter that will one non-dimensional parameter that will come into the picture, and that happens to be the Reynolds number, and we will very shortly see that indeed if you non-dimensionalize the Navier-Stokes equation, you basically get the Reynolds number only. Okay, so what I want to infer, or what I want to say, is that instead of you know what to say, instead of like varying the individual quantities differently, like changing density, changing viscosity, and then seeing what the inferences on the velocity profile would be, if I just have a Reynolds number in my equation and nothing else, I can say that, okay, if my Reynolds number is, let's say, larger, this is how my velocity profile changes. If my Reynolds number is less, this is how my velocity profile comes out to be. In fact, you see that the certain transitions from laminar to turbulence and all those things, they are not written that, okay, that this laminar to transition takes place if the density of this, because that is not universal. Because the density of water is different, the density of glycerin is different, the density of engine oil is different. So since density then depends on the fluid property, it doesn't become universal. That is something that you must understand. But the Reynolds number is universal, because Reynolds number doesn't just depend on density, it's just a non-dimensional parameter. Okay, which of course it depends on. So if you change the density, the Reynolds number changes, but it is a non-dimensional parameter, which helps us to give the range that, okay, if my Reynolds number is, let's say, for instance, in pipe flows, if my Reynolds number is greater than, let's say, 2300, the flow is turbulence. I do not say that and that is universal. I hope you realize that in case of in case of any fluid that is flowing through a pipe, if my Reynolds number is, let's say, greater than 2300, okay, I have a transition taking place into, or I have a turbulent flow taking into picture. So the idea is that if I now define certain universal quantities like Reynolds number and all those things, it becomes easier for us to basically deal with the variations in the problem, rather than changing the inherent quantities like density and viscosity and so on and so forth, because these quantities are a function of what the fluid is, and then it doesn't just become universal. So it becomes customary to define certain to define these non-dimensional numbers, and these non-dimensional numbers, you will see it just pop out of the analysis when you do a non-dimensionalization of the dimensional form of the differential equation. Okay, but and then again, in order to understand how do we basically non-dimensionalize a dimensional equation, the first thing that you need to know is known as scaling analysis. That how different terms in your equation scales uh, so as to cap so I mean, I want to say that how different terms in your equation scales such that it captures the essential physics of the problem is something that we will look for. Okay, so yeah. So since this, I understand this is something that you are just learning for the first time, so we'll try to proceed very slowly. So when I mean scaling, it means that how how the variables of interest vary basically. Or it's not right to say vary, it's I think I should write how the variables of interest, you know or it's better to write what is the ballpark figure of the variables of interest. So this is something that I want to question. For instance, if I say that I'm looking at a flow through a pipe, and if you say that how my velocity would scale, I would say that it can scale as the maximum velocity, that is the velocity on the center line, or it could be the average velocity. So it just gives us an idea that okay, the scale of my velocity is so it could be the maximum velocity or it could be the average velocity, something like that. So as I said, so we will be so what I'm trying to say is we will be looking into characteristic scales of different variables. Like, so these variables include velocity, length, time, and the fundamental quantities that we most commonly see in the equations. Okay. Okay. So without wasting any time, let's look into certain very simple examples. Okay. So let's see how can I define a characteristic scale of my velocity field. Okay. So first we will see scale for velocity. So for that, let's consider, there is a channel, and let's consider most simplistic case, that is the flow of a fluid, through a parallel plate channel. And let's say I have my axis of this form. So you now know that the velocity profile is something like this. It is indeed parabolic with a maximum at the center, and the zero at the walls because of no slip. Of course, the channel height, we will consider it as some, let's say, twice h. And this is what the velocity profile, essentially look like. So when I now ask you what is the scale for velocity, I would say that my UC, which I will call it as, so any variables with a C means that it is the characteristic scale of the variable. Okay. So UC, which is nothing but my characteristic scale for velocity. Okay. And and what it means is that for a velocity field that is actually varying in this problem in the y direction, what is the ballpark figure of this velocity field, or what is the range this velocity field could actually vary, is something that is essentially our point of interest. And for establishing that range, I also need to think about a quantity that will essentially characterize this velocity field, and this is basically what is the characteristic scale for velocity. So I can choose my UC as either the U max or the U average. Now that is up to you what you will choose basically. Okay. So in this problem, so which is where U max is basically the velocity in the center line, and U average is just 2/3 of U max in case of flow through parallel plate channels. Okay. Now what this means is that the velocity field, the actual velocity field, which is nothing but U of y, okay, its ballpark figure, although it is varying, its ballpark figure, or it's kind of an average, not an average, but it's kind of an, it's like, what to say, the more, the most suitable word is the ballpark figure basically. So the ballpark figure of this velocity is nothing but a characteristic scale of this velocity, which is just u max or u average. Now the reason why you are defining this characteristic velocity is as follows. Because if I want to now define a non-dimensional velocity, let's say u bar, which is my non-dimensional velocity, I would rather say that my non-dimensional velocity is my dimensional velocity by my characteristic velocity, which is uc. And this uc, for this problem, is the dimensional velocity, which is just a function of y. I would agree. And this uc is just u max. So this means that my non-dimensional velocity, which also is a function of y, I can now define it, okay, with respect to its dimensional counterpart divided by the characteristic velocity, which is u max. Now note that characteristic velocities are not functions of, of the space or time. These are just a ballpark figure. So these are just the quantity. It's just an estimated quantity of the actual varying quantity that we are considering. So these are not, remember, u max is not a function of time. No, that is not what we are saying. U max is like the maximum velocity of this essentially varying velocity, or you can also choose it as u average. That is up to you. So now the, you know the beauty of defining this characteristic variable is that you can straight away now infer that since this actually varying velocity is roughly of the order of this u max, this will essentially mean that my u bar, which is the non-dimensional velocity, would just be order 1. And this is the power of non-dimensionalization, okay, and choosing the correct characteristic scales for your analysis. Order 1 means, so now you must try to understand that order 1 means u bar is not exactly equal to 1. It is not what non-dimensionalization actually said. It just says that u bar is roughly of the order 1. It could be 1.1, it could be 1.5, but it cannot be 10, or it cannot be 100. That's what the non-dimensionalization basically gives us. So it means that its value will be close to 1. It may be 1, but or at max its values will be close to 1, but its value cannot be equal to 100. That is something that these notation essentially means. Okay? And you can now get a sense that when you non-dimensionalize a quantity using the correct characteristic scales, my equations or the quantities become order 1 quantities, which is also of great importance, because I don't now have to also see, if I for instance, let's say if I have a very large domain of length, let's say 100 million, okay, but if I choose my characteristic scale as, let's say, 100 million, that means the varying quantities within this 100 million will just be order 1, because my scale of length would be the dimensional length divided by the characteristic length, which is 100 million. So a 100 million length scale is now just transformed into a order 1 quantity. So you can see that how much we have. So instead of doing the dimensional analysis in a length scale of 100 million, we are now just doing a non-dimensional analysis in a scale of 1 million. Okay, so you can see how powerful it is, because just by doing the analysis from let's say 0 to 1, or let's say whatever, -1 to 1, depending on the scale we have, you can infer that what would be at the actual, so you can infer the dynamics that would actually be taking place in a 100 million length scale. That is something. So that is the power of that is the power what non-dimensionalization actually brings in this in solving certain problem. It is not only used in fluid mechanics, so it's a generic mathematical tool that people use when the equations become rather complicated. So this is one advantage of using non-dimensionalization. And again, if you want to learn non-dimensionalization, you first know how to define characteristic variables, and that's why we are learning this scaling analysis. So by now I think you have understood how basically we choose the scale for velocity. Okay, all right. Now since I was talking about length, the second discussion that I want to highlight is the length scale, or I would say scale for velocity, so I would say scale for length. Okay. So just now how we have defined the characteristic scale for velocity as UC, we will call it, we will call the characteristic scale for length as LC, which is my, characteristic length scale. Now, here I want your, little bit of attention. So once again, let's consider the prototypical, pipe problem that we, that I just now, stated. So in this problem, let's say I have a pipe length of, which is very large, let's say of L. Okay, that means that this pipe basically extends from here to here and here to here. And the width of this pipe, or not width, the height of this pipe is, let's say, twice h. So now, if I ask you what is the characteristic scale for length, you have two options. You can tell that my characteristic scale for length is the length of the pipe, or you can say that the characteristic scale for length is the height of the pipe. And these are very different because typically in pipe flows, if I have a long pipe, let's say my length is, so at least in the case where, the velocity is parabolic and the case is fully developed, the length is typically much, much larger than the width and the height. Okay. So I would say that this L is much, much larger than twice h. So this means if I choose L as the characteristic scale, or if I choose height at the characteristic scale, the non-dimensional parameters, the order of the non-dimensional parameters would differ greatly. Then which one to choose and which one not to choose is something that we will try to understand here as the length scale of this problem. The rule of thumb is that you need to understand this, that the rule of thumb is that choose the scale on which the variations are basically seen. That is, the variation of the physical quantities are basically seen, which means that if I choose, if I choose this length scale, that is, I am moving along x, I don't see a variation in the velocity profile because my velocity profile is so there is something that we learn as translational invariance. So this means that if I pick any x location, my velocity profile is just the same, it is just the same parabola. But if I choose my height as the length scale and I move, along this height, let's say, I see a substantial change in the velocity profile. For instance, the velocity is 0 here and the velocity is u max here, and it just becomes 0 on the other end. Which means that when I move along the y-axis, I see there is a substantial change in the variable of interest, which is the velocity here, and that's why we will choose the height to be as the length scale of my problem. So the rule of thumb is, as I said, that we will choose that scale as the length scale which captures the physics of the problem. That is the main main idea. Or you will see that we will choose that scale on which there is an appreciable change in the variable of interest, which is velocity in this case. Okay. So we will choose my LC as twice h or h. This is up to you because either you choose h or you choose twice h, the ballpark figure is just the same. The non-dimensional quantities, because let's say h is 1, then twice h is just 2, which is again order 1, or if you choose h, which is again exactly order 1. So this means that you can either choose twice h or as an h as your length scale, but you cannot choose the length, because if this is, let's say this is 10 meter, then this characteristic scale and this characteristic scale, the ballpark figure also varies. Okay. So I hope this is clear. So we'll choose LC as twice h or h, and we are choosing this because the rule of the thumb says that choose the length scale on which there is an appreciable change in the variable of interest. All right. So here, as I said, since the variable of interest is the velocity, and when we move along the y direction, that is along the height of the channel, okay, we indeed see an appreciable change in the velocity, and that's why we choose the length scale as the height of the channel. So now, if you define, let's say, non-dimensional y bar, which is just you know let's say it's a non-dimensional y coordinate, it would just be the dimensional y coordinate divided by LC, and my dimensional y coordinate is y, LC is basically equal to h, or it could be equal to twice h depending on whatever. That's completely up to you. And trust me, it will have no, either you choose h or you choose twice h, the non-dimensional form of the equation will just be the same. That is something that you need to understand. All right, so we saw the scale for velocity, we saw the scale for length. Now if we know this, let's see the scale for stresses. Yeah. All right, now since we have seen at least how the primitive variables like velocity and length scales as, the stretch, which is kind of a derived variable, because you need, so for evaluating the scale for stress, you need to understand the scale for velocity. And since we know the scale for velocity and we know the scale for length, it now becomes easier for us to define a scale for stresses. Okay, but before that you must try to understand one thing. So if I have a quantity x, which is of course a dimensional quantity, let's say, and if my x scale says a, okay, and let's say I have a quantity y, and see if y scale says b, see this this symbol meaning that x is not exactly equal to a, but it is similar to a basically, or the value of x is of the same order of the value of the quantity a. That is something that you can infer. Okay, then if my x scale says a, if my y scale says b, then dy by dx will essentially scale as b by a. Okay, this is something that you need to realize. And if you can realize this, then it becomes very easy to define a scale for stresses, because I can write, let's say I'm writing tau xy, which is the xy component of stress, considering the same pipe flow example. Okay, then I can say that my tau xy is just mu times of what? It is just mu times of du by dy, because I just have a u component of velocity varying along y. It's just a fully developed 1D flow that I'm considering through two parallel plates. Then I know that my u scales as uc, okay, and my y scales as lc, where uc is just u max that we just now saw, lc is just h, that is the height of the channel. Then I can also then say that my stress is tau will scale as mu times of uc by lc, just by drawing this analogy, that if my u scales as uc, y scales as lc, then du by dy will essentially scale as uc by lc. So that's it. So this is how my stresses would scale. So my stress would scale as mu times uc by lc, and since we know uc and lc, then I would say my stress would just scale as mu times u max by h. That's it. That's the scale for stress. Now, it is important to understand that the scales you are choosing, it's highly sensitive to the physical paradigm that you are considering. Okay, meaning that if you just have a different physical example, the stresses, I mean, the choice of scales could be different. So you must try to realize that. So first, examine the problem and then identify the scales is the more general rule for choosing the characteristic variables. Okay, so this is the scale for stress for this particular physical problem that I am considering. Okay, so however, I agree that the general form would just be the same. For instance, stresses would always scale as mu times uc by lc, because that comes from the very definition of stresses in Newtonian, at least in Newtonian fluids. But let's say I have a different scenario, then the choices of this uc and lc can be different. So it will not always be the fact that this will be h and this will be u max, is something that I want to say here. Okay, so this is the scale for stresses. Okay, so now that you have understood the scales for stress, and I hope so this is very primitive. Let's now look into two more scales, which is the scale for time. And let's see in a given problem how do we look into the time scale of our analysis. And time scale is very important because essentially it is a time scale that tells us that, okay, let's say I have a varying quantity. So if you ask me that how much of this quantity would be after a certain interval of time, that is highly dependent on the time scale of the problem that you are essentially choosing in your analysis. Okay, and that's why it is more important to understand the time scale. So in time scale, what we seek is, we seek the time span over which over okay we seek the time span over which there is a considerable change in the parameters or in the variables of interest, in the variables of interest. And let us see, like, what I mean by this statement. For instance, let's say I have a bird which is flapping its wings when it is moving forward. Now let's say that the frequency with which the bird is flapping its wings is, let's say, some f. Okay, or I can write it as some, let's say I can write it as f, or let's say I could write it as some omega, where omega is frequency is just 2 pi omega. Okay, and where omega is the angular velocity, meaning that if I define omega, I know that how I know the frequency with which the bird is flapping its wings. So if you ask me that in this problem, that a bird which is flapping with wings which are frequency navigating through a fluid, you ask me that how do you see the disturbances in the fluid as a result of the bird flapping its wings? Let's say I want to see the disturbances in the air. I want to see the disturbances in the air as a result of this bird flapping its wings with some angular velocity omega. So in this problem, if you ask me what is the time scale that I would choose, I would say that my time scale TC is just going to be omega inverse. Why? Because the disturbances in the fluid is governed at what frequency the bird is essentially flapping its wings. If it flaps faster, the disturbance would be stronger, or if it flaps slower, the disturbance would be less stronger, is something that we at least can infer physically. And that's why the time scale, that is the time span over which there is a considerable change in the variable of interest, which is the disturbance velocity of the air, as the variable of interest, its time scale is proportional to the frequency at which the bird is flapping with its wings. And that's why we will choose the time scale as omega inverse in this problem. Now this time scale, that is this omega inverse, or whatever frequency we have, see, this is already defined in the problem, that a bird is moving through it, let's say a quiescent air, flapping its wings at some, let's say, 20 hertz, for instance. Okay, since this is a defined quantity, we call this as the inherent time scale of the problem. This form of time scale, that my time scale is omega inverse, this is known as the inherent time scale of our problem of interest. Okay, now it may so happen that we may not have a inherent time scale. For instance, the same example, that is the flow of a fluid through a channel, that is a fully developed steady flow. We don't have an inherent time scale. We don't know the frequency at which there is no frequency, there is no there is no there is no frequency that comes in the picture if there is a laminar flow of a fluid in the fully developed region flowing through two channels. That is the same example that we saw here. Okay, then in this case, how do we choose the time scale is something that we will try to understand here, because we don't have an inherent time scale in this problem. Okay, where we have an inherent time scale, that is the first choice that would go. But here, if we don't have an inherent time scale, then how do we choose a time scale is something that we will see. So in that case, we have two choices of time scale. The first choice is I would call as the advection time scale. And as the name suggests, it comes from it comes from the fact that how a fluid advect, and we will see how what this time scale essentially is. But for that, what we will do is we'll just write the Navier-Stokes equation in the x direction to see what the advection time scale will be in this context. Okay, so the Navier-Stokes equation is what for this problem is just del u del t, let's say, and I'm just writing the full Navier-Stokes equation just for you to understand. It is u times del u del x plus v times del u del y, okay, and minus del p del x plus mu times del square u by del x square plus del square u by del y square. Let's say I'm writing, so of course if we invoke certain assumptions, certain term will go, but let's say I'm writing the complete Navier-Stokes equation at least in the x direction in 2D. Okay, now see, we are doing this because we don't know an inherent time scale for this problem. If you say me that, okay, there is some mechanism by which I am oscillating, this fluid, and we will see this through an example that if there is an inherent time scale or not. So the thing is, if there is a problem and I'm saying to you that I'm oscillating this fluid with some frequency, let's say omega, back and forth, then what is the time scale? Then I would say that the inherent time scale is omega inverse. But in this problem, at least there is no such thing that is happening. There is just a pressure gradient and there is a flow that is being taking place. So we don't know what is the time scale of the problem. And in that context, we look for two time scales, that is the advection time scale, and we will see later on the second is the diffusion time scale. So first, let's see what the advection time scale is. So as the name suggests, if you want to see what is the advection time scale, I will compare I'll see the time scale which happens as a result of advection, meaning that I will just see that how these quantities and these two quantities essentially scale set. Meaning that if my so I'll assume that the main mechanism that results in the flow of the fluid is by advection, and then I would say that my rate of change of u with respect to time would scale as u times del u by del x. And then as I said, I have a scale for u which is uc, and this is something that I already said, that if del u by del t, if u scales as uc, and if u scales as uc, and if t scales as, let's say, tc, and I want to find out what is tc, then of course if del u by del t would scale as uc by tc. Okay, so I would say that my uc by tc, this would scale as, drawing the same analogy, you can say that this scales as uc square by lc. Okay, where tc as tc is something that I want to find out, that is the scale for advection, that is the advection time scale, which means that my tc would just scale as lc by uc, and lc for this problem is h, uc for this problem is umax. So my advection time scale is nothing but h by umax, h by umax. Okay, sorry. All right, so this scale for time that you derive, we will call it as tca. This is known as the advection time scale. All right, now the same manner in which we have defined an advection time scale, I can also say that I can also have a diffusion time scale in which I can say that this term is of the same order of this term or this term, let's say. So if I say that my del u by del t is of the order of mu times del square u by del y square, then I would say that this uc by tc is of the order of mu times uc by lc squared. Okay, where uc and uc would just get cancelled, but remember, I think there is a row here. Okay, because because there is a row that is multiplied here, so the row here. Okay, and then there would be a row, I think, here. So where it is, so there would be a row here. So this means that my tc will basically scale as LC square by something which is called as nu, where nu is my kinematic viscosity, which is mu by rho. I've just combined, this mu and this rho. That's it. So this scale for time that we get by comparing these two terms, this is known as my diffusion time scale. Okay. So oops. All right. So this is known as my diffusion time scale. Now, in the same problem, that is again the same prototypical problem, that I have a flow through a pipe and I have defined two time scale. I understand that there is no inherent time scale because I don't have any frequency kind of things in the picture, but I can define an advection time scale based on the choices of the velocity and the length scale. And I have also defined a diffusion time scale, which is UCD, which is just LC square by nu, where LC is your H. So this just becomes, H square by nu. That's it. But we can only choose one scale, right? Because when you are defining a problem, you write the characteristic scales. You cannot say that there are two scales. There is just one scale. Although there are two scales that evolve out of the problem, we must choose, a single particular scale which, aptly kind of justify the analysis. Okay, and for that, what we will see is we'll take the ratio. Let's look into this thing. So let's take the ratio of these two scales, because ultimately we just need, the scale for just one variable. So for instance, I saw that my, advection time scale is what? So advection time scale is h by u max, and my diffusion time scale is is h square by nu. Okay. So what I will do is, let's take the ratio, of my diffusion time scale to the advection time scale. And when I take this ratio, what I get is, this is h square by nu by h by u max. Okay, and this h and h would get cancelled. This means what I have u max h by nu, and this can be written as nu. If I write nu in terms of the dynamic viscosity, it just becomes mu rho u max h. So what do we see? We just see that the ratio of the diffusion time scale, okay, to the advection time scale is nothing but what? So what is this quantity? So this quantity rho u max h by mu, this is nothing but the Reynolds number corresponding to the height h. Okay. So this is just, your REH basically. So the ratio of the diffusion time scale to the advection time scale of your problem simply comes out to be the Reynolds number. So it now means that, so I just have two cases here. It means that for a problem which has a very high Reynolds number, this will essentially mean that my time scale of diffusion is much larger than the time scale for advection. And if that is the case, we will choose the lesser time scale, which is the advection time scale, because the lesser time scale will capture the physics more prominently or more accurately than the larger time scale. Because if I have a time scale which is of 10 seconds, and if I have a time scale which is of 100 seconds, and the flow changes, in the so the flow typically changes in the zone of the lesser time scale, meaning that my advection time scale is the more prominent time scale if I have a problem where advection is basically dominating, because the diffusion time scale actually scales higher than the advection time scale in these scenarios for Reynolds number greater than 1. On the other hand, the other, other end of the spectrum is, if I have, a Reynolds number which is much less than 1, I can say that my diffusion time scale is much lesser than my advection time scale, and then I would choose my diffusion time scale as the correct choice for, time scale basically in our analysis. So the rule of thumb is like, always choose the smaller time scale. So that is something that I want to infer. So the rule of thumb is, choose the smaller time scale. I hope you understand this. All right. So, so similarly, so that's it. So that's the scaling for time that we have. In the same way, you can also, define something which is known as the scale for pressure, and I'll leave you as this as an exercise, and I'll discuss this in the next class if you find any difficulties. But so what I would say is that just how we found out the scale for time, we can also have scale for pressure. And what I will do is I will leave this as a homework problem for you, that consider the same Navier-Stokes equation, consider the same prototypical example of flow through a pipe, you know, consider the same advection scales of time or diffusion, diffusion scale for time. Uh, Depending on what you choose, you will see that, pressure will have two choices of scales, and you should be able to come out, what should be the scales of pressure in these cases will be look like, depending on the choice, depending on how you actually scale your pressure term basically. So that's the hint I give. I will not say much on this, but draw the same analogy that what we did, follow the same steps and the same understanding. Consider a simple prototypical flow through of a fluid flowing through a pipe, and try to find out what are the scales of pressure that we have, and then try to figure out that under which circumstances pressure will scale like as this, and which circumstances will lead to pressure scaling something else. Is something that I wish for you to do it at your end, and I'll leave this as a homework, and I'll be happy to discuss this if there are any doubts on this. But in the next class we will be solving, I'll discuss this. If there are any doubts, try to find out what will be the scale for pressure, just do the same analogy as what we did in all these things. And in the next class we'll be solving problems related to transient flow of a fluid through certain physical features, I mean certain physical boundaries, like I mean, in this week, we have looked into two cases. For instance, a plate that is suddenly set into motion, we call it as the Stokes first problem, and a plate that is oscillating basically with time, that is the Stokes second problem, and things like that. So we will look into problems similar to that and try to, solve problems that of course is relevant now to. So this is something that is not there in the assignment, but I felt this understanding must be developed for a student who is studying this course, because this is a very open-ended course where you also need to have an idea of certain things like scaling analysis and all these things, which might not directly be there in the assignment, but it will inevitably help you in the long run if you study fluid dynamics as your as one of your main courses of your career basically. So that's the idea. And try to find out what will be the scale for pressure. But yes, in the next class we'll be solving certain sums that involves transient flows, transient 1D flows to be precise. And we will see how to basically, and we will see that how scaling analysis essentially simplifies the analysis of these kind of transient problem uh, in 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 the next class. So I thank you for actively participating in these sessions and also in the discussion forum. Please keep your questions open in the discussion forum, and we'll be happy to answer them. And if you have any questions, you can ask. If no, then we will take it up from where we left in the next week at the same time using the same link. Thank you very much, guys.